Hello all the students. So today we are going to do the different type of relations. Like you must have seen that in my previous video I told you what relations are and how you can represent relations using graphical method, how you can graphically represent a relation. Now today what we are going to discuss in today's video is the different types of relations that we have in discrete mathematics. So the types of relations is the topic for today. Okay, now the various types of relations that we have in discrete mathematics are, first of all, we have a reflexive relation. So these are the different types of relations. Then we have irreflexive relation. Then we have symmetric relations. Then we have asymmetric relations. Then we have equivalence relations. And then we have compatible relations. Okay, so these are the different types of relations that we will be studying today. So I will start with the first type of relation that we have, that is the reflexive relation. Now let's start with the first category, that is the reflexive relation. So if there is a set A having elements 1, 2, 3, 4 and 5. Okay, there is a set A having 5 elements 1, 2, 3, 4, 5 from the number system. Now if a relation is from set A to itself, if there is a relationship set such that it is from set A to set itself, then on what basis will this relation be called reflexive? This relation will be reflexive if the ordered pair contains of all the elements of set A in this form. Okay, so if all the elements of set A are present in the relation in this form, that is the ordered pair consists of same elements, that is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So if all such ordered pairs are present in the relation, then this relation will be known as the reflexive relation. Now apart from these ordered pairs, it can have any other ordered pair. That is not the concern. The concern is that for each and every element of set A, they must appear in this form: 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. That means the ordered pair will have same elements. So apart from that, if you have any other element like 1, 2, or even if you don't have, that is not the concern. The only concern is that all these elements must be present in ordered pair like this, that the ordered pair will consist of similar elements. So basically we can say that the ordered pair is of the form A comma A, which belongs to the relation such that this small a belongs to the set A. So the small a is here representing the elements of set A. So for all the elements of set A, that is for 1, 2, 3, 4, 5, for all the elements of set A, the ordered pair in the relationship must be of the form A comma A. That means similar elements in the ordered pair like 1 comma 1, 2 comma 2 and so on. So if all such elements appear in this format, then the relation is said to be reflexive. Other than these ordered pairs, if there is any other ordered pair, it's okay. But our main concern is to see that all these elements appear in this form. Now, if in case I have the ordered pairs in this form, so 1, 1 is here, 2, 2 is here, 3, 3 here and 4, 4 is here. But still I cannot call it reflexive, because what did I say? That for every element of A, and here every element of A is not being considered. Here 1 is being considered, 2, 3 and 4, 5 is missing. So in that case, this is not reflexive. So you have to keep in mind that this ordered pair, this pairing will be for each and every element of A. So even if one element is missing, then it will not be called reflexive. Then if I talk of irreflexive, irreflexive is just the opposite of reflexive. If I consider the same set A, then the relationship for irreflexive will be having any ordered pairs other than in this format. That means if for every A, that is for every element that belongs to set A, the format or the format like A comma A will not belong to the relationship set. That never in the relationship set will you have any element which will be same in the ordered pair. So it can be 1, 2, 1, 3, 3, 4. In this case it is irreflexive. But if I suppose I have one element like this, I have one element like this, 3 and 3. So in this case it will not be irreflexive. In this case I cannot say that this is irreflexive because the condition is for every element, every A that belongs to set A. This condition should apply that A comma A does not belong to the relationship set. But here in this case, this thing is being violated for the element 3. Okay, so I cannot say that this is happening for every element. For rest of the elements, the ordered pair consists of different elements, but for the element 3, the ordered pair consists of 3, 3. So the rule is being violated because I say that for every element that belongs to set A, the ordered pair AA must not belong to the set R. So that means this is not irreflexive. At the same time, it is not also reflexive because the condition for reflexive is also that for every element that belongs to set A, this ordered pair must exist. So this is not reflexive, but this is not irreflexive either because again in irreflexive you have the condition that for every element that belongs to A comma A should not belong to R. So here 3 is violating this condition, hence this is not irreflexive either. But if I remove this 3 comma 3, then I can clearly see that this is an irreflexive relation because 1, 2, 1, 3, 3, 4, no element in the ordered pair is same. So you do not have an ordered pair having the same elements. So this can be an irreflexive set relation. This can be an irreflexive relation. So a reflexive relation and an irreflexive relation. Okay, now let's move on to the other types of relations, that is the symmetric and asymmetric relation. So the condition for symmetric relation is that again if I take the same set A having elements 1, 2, 3, 4 and 5, and if the relationship set is from set A to itself, then what is the condition for symmetric relation? That if an ordered pair 1, 2 is existing in the relation, then for every such ordered pair, an ordered pair 2, 1 will also exist. Or I can say that for every element A, small a that belongs to set A, the condition is that if for every element A that belongs to set A and for every element B that belongs to set A, if the ordered pair AB is existing, then the ordered pair BA must also exist in the relationship set R. That means if 1, 2 is existing, then its reverse 2, 1 will also exist, and this applies for all the ordered pairs. So this I can say is a symmetric relation because if 1, 2 is existing, then 2, 1 is also existing. But let us assume that there is one more element 4, 1, and now I close it. So I can clearly see that the opposite of 1, 2, 2, 1 is existing here, but the opposite of 4, 1, 1, 4 is not existing here. So in this case, this is not symmetric. This is not symmetric because the opposite of 4, 1, that is 1, 4 is not existing. But if I erase this 4, 1, then I can clearly see that for 1, 2, 2, 1 is existing, and thus this complies for all the ordered pairs that I have because one ordered pair and its opposite That's it. So that means the opposite of 1, 2, 2, 1 is existing. So I can call it a symmetric relation. Now the opposite of that is a symmetric relation. If I am talking of asymmetric relation. So again, if I consider the same set A, so the asymmetric relation set R will consist of all the elements such that if 1, 2 is existing, its opposite 2, 1 will not exist. So the opposites for the ordered pairs will not exist. So I can say for all the small a that belongs to set A and all the small b that belongs to set A, if AB belongs to relationship set R, then BA must not belongs to relationship set R. That is, the opposite of any ordered pair will not exist. If there is an opposite of even one ordered pair, then it will not be called asymmetric. So in this case, you can clearly see that this is an asymmetric relation because opposite of 1, 2 is not there. 2, 1 is not here anywhere. Opposite of 1, 3, that is 3, 1 is also not here anywhere. But just in case I have one more ordered pair, 2, 1 here. So you can clearly see that the opposite of 1, 2, that is 2, 1 is existing here. Though the opposite of 1, 3 is not there, but the opposite of 1, 2 is here. So my condition is that for every element. So that means even if for a single ordered pair its opposite is appearing, then it is not symmetric. Then it is not asymmetric because this condition should hold for all the elements of set A. But in this case, it is not symmetric either because again for symmetric the condition is that for every ordered pair, if AB, BA must exist. So if for 1, 2, 2, 1 is existing, here for 1, 2, 2, 1 is existing, but for 1, 3, 3, 1 is not existing. So this is not symmetric and neither asymmetric. So this is the concept of symmetric and asymmetric relations. So here you can clearly see this is not an asymmetric relation, but it is not symmetric either. And if I remove this ordered pair, then it becomes clearly an asymmetric relation, and this is clearly a symmetric relation. Now let's move on to the another type of relation, which is the transitive relations. So you must have heard many times that if A is friend of B and B is friend of C, then A is also friend of C. We assume that if A, B are friends and B, C are also friends and B is a common friend, then of course A and C will also be friends. So this concept is applied over here. So same set we will consider set A having elements 1, 2, 3, 4 and 5. So if a relationship set is here such that if the ordered pair 1, 2 exists and the ordered pair 2, 3 exists, then the ordered pair 1 and 3 must exist. That is, for every element small a that belongs to set A and every element small b that belongs to set A, and every element small c that belongs to set A, if AB is in the relationship set and BC is in the relationship set, then AC must also be there in the relationship set. So if the ordered pairs exist in this manner, then you can say that the relationship set is transitive. So this I can say is a transitive relation. Okay, now if I assume that there is one more relationship set 2, 4, 5 and then there is a relationship set 5, 1. So as per the transitive property, if 4, 5 is here and 5, 1 is here, then 4, 1 must also be here, 5 being the common element. But if this pairing does not exist here, then this is not a transitive element, because what did I say? That for every ordered pair AB and BC. So here for AB and BC this condition is being satisfied, but for this AB and this BC this condition is not being satisfied, because if 4, 5 and 5, 1 are here, then I cannot see a 4, 1 here, which is the which should be there as per the transitive property. So this then I will say is not a transitive relation. But if a 4, 1 is here, then I can say that this is clearly a transitive relation. Okay, now next, another kind of relations that we have are equivalence relations. Equivalence relations. Okay, so equivalence relations are an extension of the relations we have studied. So as per rule, a relation will be an equivalence relation if it is reflexive, that is, all the ordered pairs are in the format like this. For all A that belongs to set A, the ordered pairs are in this format. Then second property is symmetric. Symmetric, as per the symmetric property, if AB is there, then BA must also be there for all A and B that belong to set A, and it is also transitive. So as per the transitive property, if AB is there and BC is there in the relation, then AC must also exist for all A, B and C that belong to set A. So that means if a relation is reflexive also, symmetric also and transitive also, then you can say that it is an equivalence relation. Now moving on, the last category of the relation is the compatible relation. So a compatible relation will have two main properties, that it will be reflexive, that is, again, if there is an ordered, that all the ordered pairs will exist in the form AA for all A that belongs to set A, and it will be symmetric, that means for all the ordered pairs AB that exist in the relation, a BA must also exist for all A and B that belongs to set A. So a compatible relation will hold these two properties. The transitive will not exist here. So the only difference between an equivalence relation and a compatible relation is that a compatible relation must be an equivalence relation must be reflexive, symmetric and transitive, whereas a compatible relation will only be reflexive and symmetric and it will not have the transitive property. So that means I can say that every relation that is an equivalence relation, every relation that is an equivalence relation will obviously be a compatible relation for sure, because it will always have these two properties, that is reflexive and symmetric. Okay, so it will always be a compatible relation, but every relation which is a compatible relation need not be an equivalence relation. So this was all about the different types of relations that we have in discrete mathematics.